Is 1 minus a half really a half? Well, of course it is, but if you're a computer, it might not be quite that straightforward. Find out why that is and how it can make your testing just a little bit more difficult on this week's MetPy Monday. Hello, I'm John Lehman, a software engineer for Unidata. This week, I want to continue what we talked about last week with testing, but show you one common pitfall that a lot of folks are going to run into, and that is floating point math. So let's write a basic test. Remember, I've got two files, my mylib.py and testmylib.py. And when we run pytest, it's going to look for any file that starts or ends with the word test and is a .py file, and run the functions that have a function name that start with test as well. So I'm going to say def test 1 minus half. And I'm going to put in a doc string, see if basic math holds. Remember our 4-phase test pattern. So what is the first phase? It's setup. In this case, it's just going to be me saying the truth, or the result that we want is a half. I'm going to exercise, saying the result is 1 minus a half. So we're not calling any external code in this test. And then I'm going to verify, using an assert, that the truth is equal to the result. And there's no cleanup for this test. So I'm going to go ahead and save that file and hop over to my Anaconda prompt where I'm in the same directory as those files. I'm going to run the command pytest. We see that it ran one test and that test passed. So you might say, well, why do I need to worry about floating point? You said that 1 minus a half might not really be a half, but this test worked fine. And yes, it worked fine on my computer with my processor. It might not work on yours, depending on your computer architecture, what you're running on, what your operating system is. But let's look at an example where it probably won't work. So I'll go back here to our test file, and I'm going to create another test, which is test 1 minus the square root of 2. And so here we will see if more complex math holds. And this is not going to be very complex math at all, but in our setup phase, I'm going to specify the truth, which should be 0.293. I'm going to exercise. The result is 1 minus 0.707. I'm going to verify, where we use an assert and say the truth is equal to the result. And then we don't have any cleanup. So now let's go back to our Anaconda prompt and try running that. And here we see we have a failure. So we have 1 passed, 1 failed. And it shows us in the failure report, we tried to assert 0.293 is equal to 0.293, and then a bunch of zeros, and then a 4. So this is a result of what's called floating point error. The computer can't represent all floating point numbers exactly because there are an infinite number of them, and our machines have a limited architecture of 32 or now more commonly 64 bits. So we get these little errors out in that 16th decimal place or so. And for a lot of calculations, that's not going to matter, but when we're doing a direct comparison like this, it still fails. So we need to do some trick to get around this. Okay, so how might we want to get around this? Well, the first thing that comes to my mind is to take the difference and use an absolute difference, so it doesn't matter what the sign is, but take the truth, subtract the result, and say we want the difference between those to be less than something like 0.001. Now we need to go up here and import NumPy, so that will work. And now let's go run our test. So now we have 2 tests passing. But I will tell you, I don't really like that we're going to have to duplicate this logic every time. This is pretty dense to read. What if I want to change the tolerance universally? Yeah, I could have a more global-like variable, but this is just not real nice for me to read every time, and I certainly don't want to have to type it every time. Is it less than? Is it greater than? Your brain, after a long day of coding, might not really want to grapple with that. So there is indeed a better way, and that is by using some test helpers. So you could write your own test helpers, certainly, but I would encourage you to look around for the libraries that you're using, say Pandas or NumPy, and see what test helpers they've already written and try to leverage those, because their test helpers are probably, well, you guessed it, they're probably tested, and you don't want to have to do that, and it saves you a lot of coding time. And after all, you're trying to get to a scientific result, not necessarily to more thoroughly testing your test code. So let's write one more test. I'm going to test 1 minus root 2 with a better test method. Use a better way to test floats. So our setup is going to be the exact same. The truth is 0.293. Our exercise is going to be the same. Our verify, we're going to use a test helper called assert almost equal, which takes the 2 things, in our case, truth and result, and an optional number of decimal places that you'd like to go to. If you wanted to go to 3 decimal places, or if you wanted to go to 6 decimal places, you would specify that here. I generally leave it with the default, which I believe is 6. And then we're going to clean up, which we don't have any here. Let's go back to the top of our file. So now we need to import that test helper. So from numpy.testing, import assert almost equal. There are a lot of test helpers in numpy.testing that you might find very useful. So now that we've imported that, let's go back and run our test suite again. Now I have 3 tests and they're all passing. But I have 2 of them that are testing the same thing and maybe not, I don't want to take the computing cycles. Maybe those tests take a very long time to run, but I don't want to delete my old way of doing it for some reason. Maybe I want to keep that code there until I phase something else out. So we could either mark that test as an expected fail if it was already failing, but it's not. Or we could just say we want to skip it. We don't want to spin the compute cycles, but for some reason we're going to leave that test in there for now. And for that we're going to use another little helper function from PyTest. So we're going to go back up here and import PyTest. And we're going to find the test that we don't want to run. So this first test 1 minus root 2. I'm going to use a decorator, which starts with the @ symbol, pytest.mark.skip, and I'm going to provide a reason so that my future self or whoever reads this has to know what happened. It's a better way to deal with testing this used. Now I'm going to save that. Let's go back to our Anaconda prompt. Run PyTest once more. And now you see I have 2 passed and 1 skipped. So if you had a long test, that would definitely save you that compute time. So one last thing, and this is going to be somewhat of an exercise, is we're going to put in mylib.py, which is currently empty, a function to compute the wind speed from the U and V components of wind, and then we're going to write a test for it. So we're going to import numpy as MP, create my function that takes U and V, add a doc string, all right, and now we will return our result, which is the square root of u times u plus v times v, or u squared plus v squared, the square root of that. Let's save that and go back over to test mylib. So let's write a test function for this. And I would like you to pause the video and try to write a basic test of the wind speed function. It's a good practice to do this yourself and hit a couple of stumbling blocks along the way. Okay, so I hope you took the chance to pause the video and do that. I'm going to write a test wind speed function, and it is a basic test of the wind speed function. My setup, u equals 10, v equals 10. Truth, what is the truth here? So I could grab a calculator and calculate that on my own. Or if this were some calculation that I trusted my code was right, which is always a dangerous thing, but you have to get truth from somewhere, or I was doing some string manipulation, I can set right now truth to be anything I want, say 11. Go ahead and write my exercise step. Result is wind speed of u and v. Write our verify. I'm going to use assert almost equal truth result. And this time I'm going to specify I want it to be equal to 3 decimal places. And then I don't have any cleanup. So what step am I missing right now? Right, we need to actually import wind speed from mylib. So from mylib, import wind speed. Now let's go run the test. When I do this, we see that we don't have the correct answer. We guessed 11, and here's the actual result. Now, if I trust that my calculation was correct, I could just copy and paste right from here. But this does bring up the important point of, though I don't recommend doing that, you should make sure that your test actually fails before you just accept that it magically passed. Otherwise, maybe your test isn't doing exactly what you thought it was. If I put in something and this test passed on the first try, I might get really nervous because the chance of me guessing the correct answer on the first time is very, very low. And you want to make sure that you can indeed make this test fail. So we'll go back to our code. Change the truth value to be what we put in on our calculator and we know is correct, which is 14.1421. Save. And run again. Now we've got 3 tests pass, 1 test skipped. So I hope that this cleared up some of the confusion that you've hit if you tried to write some tests in the last week and saw that floating points don't always work, but sometimes do. It's really just a quirk of how our computers have to work with floating point numbers, and that's a fascinating topic in itself. I hope that you found this useful and have a great new year. We'll see you next year for another MetPy Monday.